See, there's so many people here still. Okay, so here's our paradigm. Lightweighting is about geometry and materials. Last week, we talked about materials. Does everyone remember the discussion there about how to design materials so that you could maximize the strength to density ratio or maximize the stiffness to density ratio? Remember how we talked about dislocations and dislocations moving through a lattice of atoms and how slowing down those dislocations allows you to make the material stronger. And that's sort of the fundamental paradigm here of how you design for strength. Everyone remember that a little bit? Just a little bit? Okay. So today we're gonna move to the other side of this equation. We're going to talk about geometry. This lecture is sort of biased in that direction. We're talking about how you fiddle with geometry in order to get lightweight, stiff structures. And so today's the third lecture, right? So that means we've got 4 more left, right, including today. So there's 4 lectures on how you design geometry, and that actually might extend to a 5th lecture if I can't get through everything in time. But
by the way,
yes,
you can do a 7th lecture. You're not limited to 6.
Can I get a parking pass or?
No, I'll get you a parking pass.
Okay, I can take the train in if it's absolutely necessary. Okay, right. So you look at any structure around you, and you realize at the fundamentals that there's really only a couple of real loading conditions for any kind of beam in a structure. So you guys look at this tripod behind you, the camera's on, or you look at a car body or a bicycle frame or a tractor or a tent or all kinds of different, anything you see out in the world that supports loading. You realize that they're made up of beams typically, and these beams can really only be loaded in a certain number of ways. There's really not that many permutations. There's only just a couple. So those couple include what you see here. So columns or beams are typically under bending, or they're under a tensile load, or they're under compressive load. Okay, they're under shear load. Okay, and the shear load can be thought of as either single shear or double shear. You can see the different kind of, I've listed it there. Whenever you design a structure, when you guys get that far, just keep in mind it's usually better to put things in double shear than single shear. Most engineers don't know that, it seems. And if you look at most suspensions on your cars, there's lots of things that are in single shear that probably shouldn't be. But then there's bending, cantilever, sort of a subset of bending, torsion, okay? And then there's buckling. Buckling is a stability problem. It's usually you have something that causes a local instability. And one minute your beam under this compression load is holding load just fine. The next minute it sort of gets upset and it just bang, it breaks and it sort of goes unstable and bends out of the way and you got a big problem. Okay, so these are really the fundamental ways which a beam can be loaded. Okay, this is really important. I want you guys to remember this. Any questions about this? Most everything you see going forward in this lecture is going to sort of be assuming that you guys understand this, that there's these very few ways that a beam can be loaded: tensile, compression, shear, bending, torsion, buckling. Okay?
Can you explain why double shear is better than single shear?
Because double shear reduces the stress at each of the mounts, and it reduces kind of a bending load at a smaller length scale. So you put the material in pure shear rather than some combination of shear and bending.
I also think of it as double shear doesn't have a degree of freedom of rotation of the whole beam.
Right.
Like the hand of a clock going around.
Right. You'll see lots of things if you start looking around. Let's see if I can do this right. This is the top one, right? So. Oh.
You were right before. Even like I had said before.
Okay.
Start on the middle board.
Start in the middle. This is the middle board, is it? Okay. You can, if you have, let's see, you just have a suspension control arm or something. It's on a pivot, and it's coming out here. This is the body side. Okay. In cars that are engineered well, you'll see that there's actually 2 structural mounts, and then a bolt through it, for example, or some type of axle. Okay, this is double shear. This is the better way to do things. Some poor designs out there, you'll see there's only a single support, and then there's a bending load that's introduced here, which puts everything under higher stress. So this is the way not to do things. Focus on this one. Okay? The way that stress is distributed as a result of these different loads of different ways of loading a beam is really important. When you have a beam that's under tensile or compression, the stress across a cross-section is linear. It's the same stress at every point in the cross-section. That changes very differently when you put something in bending. When you put something in bending, you have something in bending, and typically you can think of this as having a neutral axis of bending in the center, which is related to the centroid of the structure. On one side of that, you'll have compression. On the other side, you'll have tensile. And then the load inside the beam increases linearly as you go towards the boundaries of the material, of the bending beam, right? So the further you get away from the neutral axis, the higher the stress goes. But what's really important here also to notice is that you have this beam here, right? This one. And it has width h, depth b. So b is going into the screen here. But the stress goes up, or sorry, the stress in that beam under bending goes down with the height cubed. So as you'll see in a little bit, there's a way to take advantage of that to produce lighter structures. In torsion similar to bending in that you can think of a neutral axis of torsion, of bending, or sorry, neutral axis of torsion where the shear load is 0. And then as you go away from that center axis, the shear load increases so you hit a maximum at the outside of that tube or rod that's in torsion. Okay, and then there's a similar law here where the shear stress goes down as you increase the cross section of this rod. Let's say as you increase that, the stress goes down very quickly. In fact, it goes down to the rates with the fourth power. Just to give you an idea of what that means, I've drawn this out roughly to scale. I've done my best to draw this to scale. And what you're looking at here is you're looking at the cross-section of three different rods that are in torsion. Okay? The first rod, the blue one, is a radius of r. Then if you half that, you have the green one. Then if you half that radius again, you have the yellow one. And if you look at the shear load, the shear stress, the maximum shear stress, which is at the outer surface of this rod that's in torsion. I've drawn vectors here to show like what that shear load looks like. And if you look at this little blow up I made right here, this tiny little vector right here that you can't even really see, suppose that was the stress, the shear stress in the blue rod. Then as you go to the yellow rod, or I'm sorry, the green rod, it goes up by a factor of 4, and that's this green one right here. And then as you go to the yellow one, so in other words, you're taking the radius and you're dividing it by 4, you get this huge thing here. So it goes up by a factor of 64. So just to give you an idea of how quickly the stress at the maximum shear area, which is the outside surface, will go up as you increase in radius at the same constant torque. Okay, this shows you that. So it can go up very quickly. You can go from having something that, if you have some amount of stress that's not a big deal, and then you start decreasing the size of that rod that's under torsion, the stress can go up very, very quickly. Okay, so this is something you can use to your advantage when designing for lightweight. What this says is that you always want to use if you have something that's under torsion, a beam or a rod or tube, even if you have something like that's under torsion, you want to go to the maximum possible radius in order to lower the stress down the furthest. Any questions on this? Okay, the next slide I'm going to show you how you actually take advantage of this. So here we've got two tubes, let's say, okay, and these tubes are under bending. The top tube has an outer diameter of R0 and an inner diameter of RI1, okay, and some wall thickness of T, okay, and a length of L. The second tube has an outer radius that's 1.4 times that of the first one, but we've decreased the wall thickness by half. So we've taken the wall thickness from the one on top and cut it in half, and that's the wall thickness on the one on tube number 2. So would you guys be surprised to find out that if you use the equations for the bending of a tube, these two tubes actually have the same stiffness, but the second tube is only 0.67 times the weight of the first tube. So we've gone to a structure here that's lighter and stiffer at the same time. So I'll take a step back here, go back up here. If you want to know, so here's how this equation here shows how the stress goes down with the radius, okay? And it's governed by this equation here. For anyone who's had a beam mechanics class, you should be familiar how you get this. This is actually a tube, but we'll call it a beam. And when you design something like this, when you design a tube like this for maximum light weight, you want to increase the outer diameter to the maximum extent possible based on how much room you have to package this tube in. You want to use the strongest material you can so you can go to the thinnest wall. And that's what gives you the highest strength tube at the same stiffness. It's very powerful to do this. And here's an example from bicycles. On the right here, on my right, take this off. On my right is an old steel bike from the 1970s. Okay, this is a 1970 Colnago, a 1975 Colnago. The tubing that this frame is made from is just a normal chrome moly steel. It's probably a 4130 or 4140, something like that. I don't know exactly what it is. And the ultimate tensile strength of the steel used in that material is 800 megapascals. It's put together using brazed lugs. The minimum thickness of the wall in these tubes is about 600 microns, so 0.6 millimeters. This frame, not including the fork, weighs about 2 kilograms. In about, 2015, 2016, Chinelli came out with this bike here. It's on the left. And this bike is made from a much more advanced alloy. This is a material where they've put in all kinds of stuff to design the material to make the material stronger, to increase the yield strength or the ultimate tensile strength of the material. This has a lot of niobium in it. The niobium is in there because niobium is actually a very powerful grain refiner. It makes the grains much smaller. If you remember from our last lecture, we talked a little bit about this, that reducing the size of grains in a piece of steel can increase the strength because you make it more difficult for dislocations to jump from grain to grain. So again, you're impeding dislocation motions. They also have chrome and moly, manganese. Oh, sorry, that's supposed to be Mn there, not Nm. Sorry. And then there's nickel. So this is a highly engineered steel alloy. They're able to go to much thinner wall. They're able to go down to 350 microns, 0.35 millimeters. And the ultimate tensile strength of this material is dramatically higher. It's 1.25 gigapascals, much stronger material. And actually, this frame weighs 1.6 kilograms, so there's a substantial weight savings there. And the frame on the left, the white frame, actually is a lot stiffer than the frame on the right. So here's an example. You can very, I think, clearly see in these pictures here what's happened. They've gone to much bigger diameter tubes and much thinner wall. So because this material is so much stronger, you can go to that much thinner wall section, increase the diameter, and end up with a stiffer, lighter structure. That's what they've successfully been able to do right here. This is very powerful. Got a question?
Yeah, so I mean, I guess you can continue increasing the diameter.
Right.
And then you get more stiff, but is the limiting factor besides material torsion? Or
So there are portions of this frame that indeed are under torsion. You're absolutely right. The real limit here is actually how thin can you go. Okay, it is possible to draw tubes thinner than 350 microns, but what the risk that you run into is off-axis loading. Suppose you put your bike up against a street sign and it falls over, and the top tube, that's the part on the top there, horizontal tube. Suppose that hits a street sign, it'll dent. Then all of a sudden you have the risk of a buckling failure because you've got a point where local instability can initiate, and then you get a buckling failure. So. Yeah, so you're really limited by this sort of dent resistance, by off-axis loading and what happens to the frame if it's loaded in a direction it wasn't meant to be loaded. Question over here? Yep.
I was going to say, a few years ago, I was at Chrysler, and it turns out, the handle on the car,
Yeah.
you know, the lift up like this and you push it with your thumb up here, they had to increase the thickness of the sidewall because of the thumb.
This is the door or the lift gate?
This is the door.
The door, okay.
This is the driver's door. But they had to go from half a millimeter to 0.6 millimeter because the thumb was going to dent the car.
Yeah. And it's interesting, doors on cars, the part the door handle is mounted to actually is a non-structural area. The real structure of the door, the thing that stops another car from getting in your lap if it hits you in the side, is actually a big, huge beam that's stuck in the door. So this is an interesting point that to bring up here. So here's a car door. Okay, it's got something like this. There's actually a beam that runs inside the door here. It's a hollow steel tube, and this is what stops you from getting, like I said, another car in your lap if you get hit in the side. This is the side intrusion beam. Okay, and the side intrusion beam is typically made of steel, and the reason they make that part of steel, not aluminum, is because they're packaging limited, right? I'm sorry, what was your name again? Kimberly. Like Kim was pointing out, there's, you're packaging limited here. You can't always make these tubes bigger, right? There's a certain point where these tubes get so big that you can't move the wheel, or your legs can't go past the frame. It's the same thing here. Inside a door, you're very limited. So in this application, they have a hollow steel tube in there, and it's typically a martensitic steel. It's very strong steel. But they have to use steel here because they can actually make this side intrusion beam much lighter from steel than they can make it from aluminum. And they use this exact same principle of going to a bigger diameter and a thinner wall in order to keep the weight down. At one point, I wrote a paper where I derived a bunch of equations for what I'll call the constitutive laws of weight savings. Now, I'm not going to say this is a strictly correct thing to call it, constitutive laws. I kind of struggle with what that word means some days, but so I've gone ahead and I've tried to derive them here. But here are here in the next couple slides are what I call the constitutive laws of mass saving. So if you have two different structures and you want to replace material A or material 2 with material 1 or material 1 with material 2, these are what you could expect to get in terms of mass savings as a function of plugging in these different materials. And I want to point out that there's really two different regimes of design that we work with in here. This is design for strength and design for stiffness. Now, I put together this table here. These are kind of typical materials properties for a bunch of different common structural materials. I've come up with these numbers based on my experience and knowing what's possible and things that are available and what you actually can get off the internet easily if you need to buy something. But these are the values that I'm going to use in an analysis I'm about to show you. Now, there's people who are going to argue with these values. There's a lot of controversy here about the real magnitude of these values, but let's just take them as they are for right now. But you've got carbon fiber. This is really a carbon fiber epoxy with a 70% volume fraction of fiber. That's very high. It's difficult to get that much fiber into a composite. And then there's a high strength steel. This would definitely be a martensitic steel, but an automotive grade. Magnesium. People get excited about magnesium because it's low density. Aluminum, fiberglass, and titanium. So I think you plug these values for these materials into the equations I showed you on the previous slide. You can begin to rank the relative potential for mass savings of these different materials. And I've done that here. So you have, on the top here, you have the loading case, which is tensile, compression, or shear. And then on the bottom half here, you have bending loads in a design for strength and a design for stiffness scenario, right? Plugging those equations in and calculating out the relative opportunity for mass savings, you get these rankings here. And I think a lot of people would be kind of surprised to see the results here. So everybody, you hear titanium or magnesium or aluminum, you get all excited, oh wow, we can save so much weight with that. But in certain scenarios, that's not always the case. And that's what's really, I think, important about this table here. For example, when you are under tensile or compression and you're doing a design for stiffness, you can actually do better with steel than magnesium, aluminum, titanium, and fiberglass. That's because steel has a very high stiffness. Remember I told you before, the stiffness of steel, the Young's modulus, basically doesn't change with alloy. It stays really close to the same within a couple of percentage. And that's an intrinsic property of steel. It's really high. It's got a 200 gigapascal Young's modulus, which is much higher than than aluminum, which is like 70 gigapascals of stiffness. So if you factor in that fact, you can begin to see the potential weight savings with aluminum. I'm sorry, with steel over those other materials. Paige, you got a question?
Yes. So you have carbon fiber winning in every category.
Every category.
But that's based on your 70% fiber.
Right,
to carbon.
which is high.
Right. So what if you used a lower, like a more reasonable, I don't know what a more reasonable number is, but maybe like 50%?
Yeah, probably like 40 is more reasonable.
And in that case, does carbon fiber still come out on top in every category?
No, but here's the good point. Now that you have these equations, if you're really interested, you can go off and try this yourself, because it's a fun game. I've played this a lot. I have a spreadsheet. I'll give it to you if you want it. Kind of nerdy. What's that?
I'd love to have a spreadsheet.
I'll give you my spreadsheet. But no, I've played with this a lot. Like, how strong do you really need to get? How stiff do you really need to get in order for carbon fiber not to win? But there does get to be a point where you can actually do better with steel than you can with carbon fiber. And like fiberglass is another example. Like fiberglass is horrible in stiffness.
Right.
And that's why it's number, it's the last one. It's number 6 here. Designed for strength. So this is another place where things are very variable, right? Because it's not impossible to get steel with a yield strength that's above 1 gigapascal. And once you're at that strength level, you can beat out magnesium and aluminum very easily in a design for tensile, designed for strength. The world changes very much, though, when you go to bending. And this ratio of yield strengths is to the square root power there. That's when things become very different. Once you get under bending or torsion or buckling, it's very hard to beat aluminum. Steel goes to the bottom very quickly once you put in that nonlinearity. So this is a graph for a solid beam. I mean, this is a table for a solid beam. And here's the rankings here also for torsion and for buckling. Again, steel comes out on the bottom. And then here is for tubular structures. So these numbers are actually, for bending, they're slightly different because the equation changes when you have a hollow structure. But the relative rankings are very close to the same. But I should be making, I need to give you a copy of this so you can put it on the website, right?
Well, if you want, yeah.
Yeah, so that they can look at this, because I'd like to, you guys really should take some time, if you had some more time, to look at these rankings and see what the real, like I said, what the real world mass potential savings is. Because like I said, a lot of people hear aluminum or titanium or magnesium and they melt and they figure you can save all this weight, but steel is surprisingly good. And you guys probably think of steel like they make big bridges out of steel and boats out of steel, and it's just some old kind of material that no one's looked at for a while. And the real world is about aluminum and titanium and magnesium. That's how you reduce real weight. But it's not always the case. A lot of times you can do a lot better with steel than I think most people realize, and that's because of its intrinsic stiffness, and it's because you can make it really strong. We know a lot about steel. The material science community knows a lot about steel. They know ways to design steels so they're really strong, and you can take advantage of that strength to reduce the weight of a structure. Okay. Who's seen these before, the Ashby diagram? Okay, I love Ashby diagrams. I've spent a lot of time staring at these too. An Ashby diagram is sort of a region plot. You plot out Young's modulus versus strength, or relative Young's modulus versus relative strength. There's a whole bunch of these. He's got fracture toughness, he's got thermal conductivity, and you can begin to draw on these regions, okay? These regions of where different materials would end up if you plotted them out. Bubble, jelly beans. Where all the steel family going to end up? Where's all the aluminum going to end up? You can begin to look at these graphs very quickly understand, which materials are going to give you the best ability to reduce weight for different design scenarios. Effectively, these graphs are really the same thing that I showed you here. Exactly the same thing, it's just plotted on a graph. Ashby uses these things he calls materials index, M. And these materials indexes are really sort of one side of these equations. You want to maximize these materials indexes, M. And on these Ashby plots, typically they'll put these different lines here, right? So there's these lines right here. I don't know if you guys can see this or not, but there's these dashed lines here, and at the end of the dashed line there's an equation. Those equations correspond to tensile or bending or torsion or any of those different loading cases I showed you. And you begin to think about drawing lines that are parallel to these lines right here. And then the further the line goes up towards that direction, the higher that materials index. Then you can be able to line up that line with the bubbles. And then you can understand these are the materials that give me the most possibility of reducing weight under those different loading scenarios. There's a great book. Ashley has a great book on these, and you can you can look up all kinds of different tables, all kinds of different Ashby diagrams for different properties. Can't remember the name of the book, but let's see. I think Granada Design is a company that Ashby started, where they worked on selling this information and how to use them, and they recently got bought by ANSYS. So you can learn more about this. This is a great tool to have.
Is it material selection and mechanical design?
You know, I have the book, but I can't remember what it's called. But it's you have it. It's a great book. It's a great book.
Got 5 books.
There's 5 books? Okay, I thought it was only one. Good for him. Okay, so we've talked about bicycles, right? And now we're going to step it up a little bit in complexity. Here is a car body that's been broken down into those fundamental beam structures. Okay, so bicycles only got about, let's see, 1, 2, 3, 4, 5, 6, 7, about 7 tubes, maybe 8. Okay, and then but a car body is far more complex. It has to take many more loading conditions than a bicycle does. Bicycles typically aren't designed for crash. I think the manufacturers figure if you crash, and that's your problem. There's no government organization that's trying to keep you safe in a bicycle crash. They're trying to avoid bicycle crashes maybe by making you put reflectors on. But anyway, so here is a body structure of a car broken up into its kind of individual pieces, beams. So here we've taken a structure that's very complex. We've broken it up into individual pieces. If I go to the next slide here, I'm going to come back to this. This is a. We got more books? Okay.
I got 5 books.
You got 5 books.
You can pass them around if you want.
Thank you. So here's on the left here. This is what's called a body in white. So this is they call it body in white because it has something to do with they make these parts from stamped steel. They spot weld them together. Then it gets painted in a primer. The primer's white, so they call it body in white. But this is a body in white structure. So the primary structure of a car from a what do you call it? A mid 2000s Mercedes C-Class, and it looks pretty complex. But if you distill this down to the fundamental parts, it really is just the same as this right here. And what you're looking at here is you have a structure that has a rocker section. You've got a front bumper. You've got rails, inner and outer rails. You've got different pillars. The A pillar is the one that's sort of right. When you're looking out the front of the car. When you're driving, it's right up there. You can touch it with your hand as you look forward. There's the B pillar and the C pillar, the rear bumper. There's various cross members here. There's seat cross members. There's the cowl cross member. The cowl cross member would be like where the windshield wipers kind of roughly go. There's the seat cross member where it's kind of behind the rear seat. And the shock towers, that's where the suspension loads, the springs, the shock absorber package feeds into the body structure. And there's all these different little pieces here. There's roof bows. These various parts are there to make the car body structure stiff enough so it handles and rides well, and they're there to protect you in a crash, whether that's a front impact or a side impact. That's what that's how this whole thing is designed. Looking back at this, when I showed you before, this slide here, we can then begin to identify between these two what are these various different parts of the body structure. So there's the sill section, the rocker, front bumper, A pillar, B pillar, C pillar back there, roof bow. This is actually a car with the sunroof, so it's a little bit more complicated. Front roof header, that's the cross member above your head, and inner rails, seat cross member, rear suspension cross member. Okay, the crush cans right here. So most cars today actually have what's called a crush can. It goes between the front rails and the bumper, and they usually make this part out of aluminum. They take advantage of some of the deformation mechanisms in the aluminum to absorb more energy in a front impact. So body structures on cars are loaded in very complex ways. They are loaded under torsion, for example. So take the whole body structure and twist it. Okay, that torsion load has a lot to do with the way the vehicle handles. A a body structure that is not stiff in torsion will not have as crisp handling as a car that is stiffer in torsion. Then there's bending loads. Okay, so a bending load is sort of, you can imagine, like if you the way they test this is they actually put a pole across like where the front seats go, and then they hold the car by the suspension mounts and they push down. That puts the body structure in 3-point bending. 3-point bending is very important for the way a car feels in terms of if it's comfortable. If you hit a bump and it rattles a lot, for example, or doesn't, or you hit a bunch of bumps, here in Boston, that's especially relevant, right? Yeah. It's okay. So some other loading conditions that the cars are loaded under. So front impact, cars are loaded. Obviously, they're designed to withstand a front impact. Rear impact, cars are designed to withstand rear impacts, side impacts, and rollover, for example. Okay. Here's a zoom in of torsion and bending. How the body structure would be loaded in these under different loading conditions. So if you understand that there's these loading conditions that the car is loaded under, the body structure is loaded under, it's possible then to think about how each of those different structures, those different beams are loaded, whether they're in torsion, compression, bending, buckling, or a combination of three or one or the other. At that point, it becomes very possible to line up the results from this table, right, or these tables, with what makes sense in here. Make sense? Okay. So in doing this, you can understand, like all of a sudden, it makes sense. If you have only so much money to spend on aluminum, because aluminum costs more than steel, where do you put it where you're going to get the biggest bang for the buck? Where are you going to get the most advantage of putting these higher cost materials in different parts in the vehicle? Okay. Yeah, Kim.
Some of them are to the power of 1/3.
Right.
Maybe for just straight ratio between the two. Do you just choose the design factor that gives you more, like that has more of a failure?
So those factors that you're talking about, the 1/3, the 1/2, that's related to the mode of loading, whether it's under bending, or torsion, or buckling. So you have to go ahead and then analyze. You have all these different tubes that make up the body structure, and you know that under certain loading conditions, they're under bending, they're under compression, they're under tensile, they're under buckling. Then you can go ahead and use that table to plug in which materials make the most sense based on what they're loaded, how they're loaded.
In what way would there be torsion?
For example, if this whole body structure is under torsion, right? So if you think about grabbing it by the wheels and twisting it like this, okay? These inner tubes, the inner rails are under torsion.
That's just if there's only ground.
No, actually, when you go around a corner, there are forces that twist the body structure. They almost like matchbox it, if you know what I'm saying. They kind of shear the body structure. That's a torsional load. That's a global torsion load. And that puts these inner rails under torsion. That's one example of where there's something in torsion. But hitting a pothole also would put the body structure under torsion. Because it's not hitting one wheel, right? Probably. It's a small pothole. Okay, so that's what I had for lecture 4, or lecture 3. We might as well move on to lecture 4 since we still have another 15 minutes.
That's fine. I was going to give one other example.
Another example. Baseball bat. Okay.
This is what I use. The alloy is a scandium aluminum alloy, higher strength than anything in any aircraft. The problem with scandium is it costs $10,000 a pound. Okay, to alloy it. Or that's the cost of the scandium.
Right.
The other thing is you want to match the stiffness of that bat where it hits the ball to the ball. You get the maximum energy transfer, momentum transfer. That's freshman physics. Okay?
Right.
And so that has to be very thin, but not so thin that it won't crush. And in fact, that is the problem. They can get it thin enough that it'll last for one hit before it crumples by buckling.
So that's one of the scandium alloys?
It's a scandium alloy. It says scandium on it. It's painted on there, but it is a scandium alloy. It's 100 KSI aluminum, or if you want to say it, 700 megapascals.
So that's pretty strong.
It's stronger
For an aluminum.
than anything Boeing uses.
Wow,
Anyway,
pretty impressive.
I would say sports equipment, whether it's bicycles or other things, or actually the most expensive of all is golfing equipment. Golfers are older men who have a lot of disposable income and will pay anything to have an advantage over their peers.
Bicycles aren't much different for the same reasons.
Younger men and women.
Huh?
Younger men and women.
No, I was just going to say, like, people will spend all kinds of money to take a gram off their bike rather than, maybe leave one water bottle at home.
That's dangerous.
Leaving the water bottle at home?
Yeah. I mean, dehydration is the big issue.
Well, depends how far you're riding, I suppose. Okay. You guys see how the body structure works here? Concept, again, you can break the body structure even though it looks pretty complex into different tubes. These tubes can then be, you can think of these tubes as being in compression or tensile or torsion. And then by using the tables with the constitutive laws, you can then plug in materials that make sense. And this leads to the idea of building body structures with multiple materials so that you get the maximum weight savings at the lowest cost. Audi has done this to great effect on the Audi TT, I think, that's currently in production. They use steel and I'll show you this later. I've actually got a slide for this later. They use steel in the rail sections to take up the torsion load and the bending loads and the front impact and the rear impact. And then they use aluminum as a closeout panel because they don't need that much mechanical capability just to keep the wind and the water out of the passenger compartment.
So what you've talked about here is like the loading of the vehicle. Is there also designed like vibrational modes, mode shapes?
Right. So what you're talking about is the natural frequency of the vehicle.
Is that a bit less of a constraint than the loading, or is it?
Well, it's the same thing.
Play into the design.
So that's when I showed you there was torsion load and there's bending load. What I didn't say is that they do more than static testing in that condition. They do both static and dynamic testing. And you're right. You always want to increase the natural frequency as high as possible because you're trying to get at a frequency that's beyond something that'll resonate with the road. Some type of road input from, I don't know. You're right. Those little dots they put in the road, the reflectors and things. What are they called? Junk bumps. I just call them reflectors. Anyway, the reflectors. Like if you're driving over a whole series of those things and you're some frequency input of the body structure, you don't want to hit that same resonant frequency with the body structure. So that you try to stiffen up that body structure as much as possible. So you're always at a much higher natural frequency than you would be hitting with those little eyes. Mid-20s is usually, 20 to 50 hertz is usually kind of what you get with the body structure in a car.
You want to talk about NVH?
Yeah, that is NVH. Is exactly what we're talking about. So NVH is noise, vibration, harshness. It's sort of a generic term made up in the auto industry to engineer cars so that they are comfortable. Their noise, vibration, harshness is good. It's can be a very qualitative thing. I wish they would do it more in airplanes, actually. It doesn't seem like the aerospace industry has found out about this. These planes certainly aren't designed for NVH. Here's another one that's interesting. You think of tire construction. So when tires are made, they have a casing that wraps around. And there's always a little tiny bit of overlap right here where the belts and the tire come together. And as the tire is going down the road and spinning, you hit this little overlap, and all of a sudden the wheel's not round there, and you get a little input into the body structure, little vibration. As you go faster and faster, that frequency goes up because this little overlap and bump here is hitting the road more often. Now, this means that this could also cause a resonant frequency in your body structure if it wasn't stiff enough. And as you go faster and faster, that frequency goes up. So if you're trying to keep your body natural frequency above the frequency from this road input, from this overlap, and you want the car to go faster and faster, like in Germany on the Autobahn where there's no speed limit, certainly parts of the Autobahn, there you run into a problem because as you go faster and faster, this frequency goes up and your body structure stiffness has to keep going up higher and higher. That's one of the reasons that Germans historically have had much stiffer body structures than American cars because they've always been so paranoid about this frequency getting into the vehicle and causing discomfort from an NVH perspective So as a result of that, they've always chased making the body structure stiffer and stiffer. But what was your name? Matt? Matthew. But to Matt's point, though, is that this is exactly what I've shown you. How do you design? This is your design for stiffness scenario. When you're talking about this dynamic loading and what inputs are going to the body and what's the natural frequency, that's the same thing as saying stiffness. So you want to keep going stiffer and stiffer and stiffer, right? So that makes sense. Then you begin using those design for stiffness things. And that's the place where you'll never win out with steel, except for tensile loading, right? But with bending, torsion, buckling, that's the place where you start doing better with aluminum, like I said. And this is where you start using exactly what I've shown you, is how not to get into those resonant frequencies, how to stay away from those resonant frequencies. Okay, does anyone understand this? Any other questions? We might as well move on to the next lecture if we're gonna. Might as well. Okay.
They don't know where it begins and ends.
I know. I just it's hard to know what exactly you can cover. Okay, so I'm going to explain this example right here, and then we're going to probably have to call it a day. Okay, so you have a column, a tubular column right here, that's under compressive load. So this has the risk of, can anyone say it? Starts with a B. Buckling, right? Local instability. This could buckle. This is a tube. It has a diameter of d0. It has an inner diameter of di, and a thickness of t, wall thickness of t. You can very readily, as you know, calculate out the weight of this tube using that equation there. So the density times pi LDT. That is the cross-sectional area of the tube, okay, times the density gives you the weight. That is the weight of this tube. You're given the job of finding the minimum weight of that tube. How do you do that? You have side constraints. The diameter can only be so big. The thickness can only go so small because you have some limitations from, like Kimberly pointed out, you have some limitations there from some type of off-axis loading. And then you have to have a ratio of these two because you have to draw this thing of the diameter to the wall thickness. So you know that you don't want this guy to buckle, right? And then here's the classic equation from Euler on buckling. And then there's local buckling, so global buckling and local buckling. And you know that this thing, there's some stiffness that the material, because it's made out of aluminum. There's a length of it. There's how big the load is, P up there. And then there's the density of the material. Okay, understand the scenario? You've got a tube. It's under some compressive load. You're concerned it's going to buckle. You don't want it to buckle. You want to make this as light as possible. You've got certain variables. How do you figure out what is the lightest tube you can go to that won't buckle given the loading of 5,000 pounds? Got the scenario? This is the question. This is the problem. Your boss said figure this out. This is what we would call having a design space of two variables. This is the thickness of the tube, the wall thickness of the tube, and the diameter of the tube. So let's plot this out. You've got the bottom axis here, you've got the diameter of the tube. On the vertical axis, you have the thickness of the wall. And then, given those two parameters, and knowing what the density is, you can very easily begin to plot out contours for weight. Okay, so these contours here, this one, this is the weight of the material given those combination of parameters. The weight is going down as you're going this way. Does everyone see that? Then you can start putting your constraints on this same graph. For example, the diameter, big D, has to be less than 4. So you know you're going to have to be that side of the constraint. The thickness is also constrained right there. And then there's these constraints for Euler buckling. That's this graph right here. Okay? So here's the line for buckling. Here's the maximum tube diameter, which very, very clearly shows you that your lowest weight solution is right there, point number 1. Okay, so you've got what I want you to really understand about this graph, because this is going to be important in our next lecture. You've got a two-dimensional design space. You've got two variables that you can mess with in order to create the lightest solution that carries the load. Diameter and thickness. You've got constraints. Okay, the constraints are the diameter of the tube, and you don't want it to buckle, so that's the other constraint. You've got G here. You can think of plotting out these constraints on top of weight on this two-dimensional design space, which very quickly leads you to a solution. What the latest weight solution is right here at number 1. Okay, we're going to scale this up later on. We're going to talk about in terms of millions of design variables. How do you find the optimum when you have millions of variables? That's what we're going to talk about in the next upcoming lectures. And that's where the math gets kind of sticky, and it all becomes very, very dependent on some very theoretical math. Kim?
You had mentioned there's two constraints, right?
Right.
You said one was buckling. What was the other one?
It was global buckling. That's Euler buckling, which is G1, and then there's local buckling, which is G2. The red line is G2. Okay, and then this line right here, this kind of teal line, this is G1, right there. See that?
Yeah.
Okay, again, two-dimensional design space with constraints G1 and G2, and then constraints on the geometry. When you plot this out on a graph like this, it's very easy to see where the latest weight solution is, which is right here. You have to be to the left of the G1 constraint. You have to be to the right of the diameter constraint, and then the weight is going down because you've got these constant weight lines. These this blue one, and then the purple one, and the green one. As you go this way, the weight's going down. You have to be between these two curves. Very clearly, you begin to see real quickly that your lowest design is right here. It turns out that the G2, the local buckling constraint, was unimportant. It was less constraining than the global buckling. Okay, I'm going to stop right there. And like I said, in the next lecture, we're going to talk about how do you use the same principle, which looks very simple right here, for finding the minimum weight of that tube. How do you scale that up when you've got millions of variables?